Okay, let's get started. This video is about atmospheric seeing and transparency, and it's the first part of a series I'm calling Which Camera is Right for Me series. So if this is the first time dropping into the channel, welcome, and everyone, you know the drill. Like, subscribe, and share. All right. So a little bit about what the series is about. I'm looking to purchase a new camera, a dedicated astro photography camera, a monochrome camera. I knew when I was doing my research, trying to decide whether or not I was going to jump into deep sky object imaging, that I was in a light polluted area. I also knew one of the solutions would be to go to a monochrome camera and filters. This video is not about that, but overall, the series that I'm putting together is sharing how I'm getting to the decision on which camera I'm going to buy. But a couple of key things here. You know, I made the decision to get started with my Canon 6D, and it's allowed me to get started and do imaging. So really, whatever you have as far as a camera, get started. The best thing to do is get started with it, start to collect some images, start to evaluate your images, and then make some judgments about your camera. Is it acceptable? Is it going to allow you to produce the type of images that you of the quality that you want to produce? But again, the key thing is get started. As always, I'm a beginner, so the information I'm presenting is high level, and it's what I believe to be important for me to make the right decision about purchasing a dedicated astronomy camera for myself. And I'll list the references I used, which is the foundation for the information I'm going to share with you here. But most important of all, you know, there's rules, but the most important rules of all is have fun, learn, adjust, and share your knowledge with other beginners in the community. And let's just take a moment. What does it mean to be a beginner? And keep in mind, you're an experienced beginner. Yes, just like me, we're just starting out to learn a new skill or take part in a new activity. But I don't know about you, this is not the first time I've learned something new. And therefore, we can leverage our prior experience gained through learning new skills and activities and apply that process to the deep sky object imaging domain. So I like to think of myself as an experienced beginner. I've begun many things in my life, so I'm going to leverage what I learned through being a beginner in those situations and apply it here. And most of all, what I've learned is how I learn and how I learn best. So I'm using an agile approach to going up the learning curve. What that means to me is I identify a slice of knowledge that I want to learn. I create a plan on how to learn it. I execute that learning effort, and then I review what I've learned and I repeat the process. And so there's a tremendous amount to learn in astrophotography, deep sky object imaging. Tremendous amount. So what works for me and may work for you is to slice the knowledge areas up. Take little slices. Try to figure out what slice to start with first and then build other slices on top of it. But chunk it down. Learn small areas, slices, and go through a process and apply it. So you may be a beginner like me, but maybe you're an advanced beginner because you've begun stuff before. So anyway, I just wanted to throw that out there. I read a lot of forums where someone will say a more experienced person, for beginners, they should do this or they should do that. And it's often good guidance and everything. But again, we haven't begun before. Many of us have begun many times. So anyway, a little bit of my pontificating maybe about what it means to be a beginner. All right, so let's get into transparency first. And their air has opacity. There's particulate in it. There's smoke pollution. If you're in California like I am, sometimes of the year there's a lot of smoke from the forest fires. Or, maybe you're in a very humid area where there's a lot of moisture in the air. These are all things that can impact the transparency of the air. And poor transparency even makes light pollution worse because it's got stuff in the air, scatters the light pollution around, bounces it around instead of letting it escape up into space. Generally, your transparency will become better as you gain altitude. As you go up in altitude, the air is less dense, or another way to say it, there's less air. So oftentimes this is a positive. Altitude is a positive. And transparency is generally better after a rainstorm. I don't know what your experience has been, but I know often here, while we don't get rain a lot, when it does rain, like it's been raining the last couple of days, when I go outside and I kind of look towards San Francisco, I've got a much cleaner view of viewing the skyline of San Francisco. So the rain, oftentimes knocks the particulates out of the air, and that's a positive thing. Now let's get into atmospheric seeing. We hear this term, or at least I hear this term a lot, seeing. So really, what does it mean? It's just a measurement of atmospheric turbulence. Air is like a fluid. Air moves. Different things move the air. And therefore, with this turbulence, we can get blurry stars and blurry deep sky objects due to this turbulence in the air. And seeing is measured in arc seconds, not a time period, but an angular distance that describes the distance on a celestial sphere. So if seeing is 4 arc seconds, it means stars should be expected to be jumping around. It's why oftentimes people say stars twinkle. That atmospheric turbulence, the seeing conditions are such that the star appears to be moving around a lot. And it goes to reason that a seeing value of 1 is 4 times better than a seeing value of 4. And generally, as your seeing conditions improve, your stars become less bloated and you get finer detail because that turbulence is lower and not causing an issue for you. The other thing when it comes to seeing is it's generally better where the geography is flat. At one time I lived in Illinois, outside of Chicago area. It was a very flat topology. I am now living in a portion of the Bay Area to where the west of me there's a range, a coastal mountain range. And so while mountains are better for transparency, again, because when you go up in altitude there's less air, they are also can cause turbulence in the air. Winds coming over mountain ridges can cause what's known as mountain waves, where it pushes the air around. And so while you're gaining some benefit by being up in altitude, if where you are up in altitude is on a mountain range, then you're going to get some issues from the airflow coming over the mountain range not being stable, and again it's very turbulent. If we look at where some observatories might be in the Pacific, yes, they're up on a high peak, but there's nothing but flat ocean generally around that island. So they're not getting as much turbulence from the effects of mountain ridges and those type of things. So, given poor transparency and poor seeing, generally being in poor seeing conditions is going to be a more limiting factor on the quality that you're going to get out of your astro images. So, just maybe to recap, you want to familiarize yourself with seeing, atmospheric seeing, the turbulence, and the condition known as transparency, and start to understand their relationship, and then how that relationship interacts with the pixel size or pixel scale of the camera you're doing to image with. So generally, as we know, the camera pixel captures the photons or the light from the objects that we want to image. And as a general rule, larger pixel scale, larger pixel size has many benefits in one sense. There's more room for error when you're guiding, which means there'll be less likely that if there's some backlash and error in your guiding, it'll be less likely that you're going to get as pronounced star trails. So therefore, there's really a battle when you start thinking about the benefit of a large pixel scale and a smaller pixel scale, because the smaller pixel scale should give us a finer resolution on our images. And I'll go into that in a minute when we take a look at arc seconds per pixel as it relates to different pixel sizes. But then again, on the larger pixel size, given the focal length of your telescope, you may cause a condition called undersampling, where you're not sampling enough. And maybe one way to look at it is when we're taking pictures in the daytime with a high resolution, 20 megapixels, 16 megapixels, whatever, and then we are viewing that image and we want to zoom into it, we continue to see a fine detail as we zoom in. If you're undersampling on your astro images, it's my understanding as you start to go zoom in, that resolution, you kind of lose it, and things become a lot more blocky looking. Pixelated might be a term. So the important thing, though, is pixel scale. Having a smaller pixel scale does not necessarily mean you will capture the finer detail you expected from the smaller pixel scale. And the reason that is, of many reasons, is because of atmospheric seeing and transparency play a role in achieving clear astro images. And so you should be considering seeing conditions in your area and transparency conditions in your area, along with guiding conditions of your mount and how much error it may have when selecting a camera pixel size. So what I'm finding out in looking for the next camera is there's several factors that really have to be balanced out. It's just not pixel size, it's pixel size, it's focal length of my telescope, it's seeing, atmospheric seeing conditions in the areas where I plan to image from, and it is transparency conditions in the areas I plan to image from, and where I thought it might be good to head back up towards the Truckee area of California where I once lived at one time because I'd be higher in altitude. Well, lo and behold, I've learned that the airflow over the mountain ridges will make the air unstable. There'll be turbulence, mountain waves, and eddies, and all these dynamics that may negate the benefit of being up in altitude. So I'm not saying I'm overwhelmed. I'm saying I'm trying to understand all the variables that can impact my ability to get a good image with the resolution I'm looking to get when it, and we're just talking about the data acquisition side of the equation, because then there's the whole image processing side that also plays a role in the quality of your image. But when it comes to resolution and the finer detail in your image, definitely the relationship between pixel size, seeing, transparency, and guiding are important considerations to understand in trying to get to the right decision. Uh, Here's just a little table that I put together to maybe share and explain how we get to the pixel size in arc seconds. And again, the pixel size in arc seconds, one way to think about it is it's the amount of sky that one pixel will cover. So if we look at my Canon 6D at the 6.54 microns pixel size with my 360 millimeter focal length of my Zenith Star 61, the resulting pixel size in arc seconds is going to be 3.74 something. And I just want to mention this 206 number there is a factor that people use. I don't really understand how it was derived, but it's an accepted factor to use when trying to get to pixel size in arc seconds, taking pixel size microns and the focal length into consideration. And then as you see, as I go down, my Fuji X-T1 with the slightly smaller pixel size is going to have a smaller pixel size in arc seconds value. So again, starting to work towards finer resolution, less angular sky space per pixel, I believe, if I'm saying that right. And then the bottom two are dedicated Astrocams, monochrome cameras, and their pixel size are even smaller than my XT1, with the QHY 183M being the smallest. ZWO has a 183M, I think, that uses the same Sony sensor, which has a 2.4 pixel size. And again, just briefly, while I was looking to go with the smaller pixel size of 2.54 or 2.4, thinking that I'm going to increase the resolution in my astro images, that was really before I started to dig into the impact of seeing conditions and transparency conditions as to their effect on whether or not I would gain the actual benefit of going to a smaller pixel size. I've decided, along with still not knowing how much real guiding error there is in my Skywatcher HEQ5 mount, that going to that small of a pixel size is not the right thing for me to do. So that got me started looking at the QHY 268M, which has the larger pixel size. So what I hopefully, we're not done yet, I'm going to go to another screen and show you a chart you can use to help determine the forecast for both seeing and transparency in your area. But I just wanted to help to share that you can see as pixel size changes, your pixel size in arc seconds changes as well, and this is a consideration when trying to pair the pixel scale or pixel size of your imaging camera with the focal length of your telescope. So again, pixel scale, focal length, seeing, and transparency. In my mind, what I've learned is there is a relationship there, and it's important to understand that relationship. And again, arc seconds is not a time period, it's an angular measurement, and it's 1 arc minute is 1/60th of a degree, and 1 arc second is 1/60th of the arc minute. And so really, in simple terms, it's the amount of sky which will cover 1 pixel on your camera sensor, and that's why you saw the values going down as the pixel size got smaller. Pixels per arc second went down correspondingly. The reason we should be interested in that again is because the Earth's atmosphere can impact what we can achieve in our images based upon pixel size. And for most locations, on a good still night, minimal turbulence, a seeing of 2 arc seconds is pretty good. Oftentimes here, I think the seeing is more in the 2 to 4 range. Again, because of impact of mountains, airflow, heat islands, all kinds of things that can make the air rise and become turbulent have to be taken into consideration. So I think in kind of just summarizing, in order to get the most results from your equipment, and by most results is getting the best clarity in your astro images with the correct level of finer detail, you need to match your resolution of your camera as determined by pixel size to the resolution of your optics as determined by focal length, while taking seeing and transparency conditions into consideration. So hopefully this made sense, but I guess what I'm admitting is I just kind of went off in a direction thinking, oh yeah, man, I'm not getting the resolution I want to see in some of my images with the 6D. I just need to get a smaller pixel size. Well, it's just not as simple as that, as we will find out in this area of deep sky object imaging. There's some other variables that we always have to be mindful of when making some of our decisions. So hopefully this helps a little bit. And now let's just kind of flip over to this other view here. This is called a clear sky chart. And let me see if I'm going to cause a problem by moving this display over here. Okay. So again, I'm going to put the references that I used as a foundation for the information. So there'll be a link to this as well as a link to some of the articles that I read, so you can read them yourself and draw your own conclusions. But here we have a forecast for San Mateo on the clear sky chart. And what we have here is top row is cloud cover, then we have transparency, and then we have seeing. And it also gives you some information on when darkness is, and then some indications on smoke, wind, humidity, and temperature. I haven't dug into this tool in full yet, and there's a lot of information on how do you read it. Again, probably a better explanation on transparency and seeing than I was able to provide. How to read smoke, humidity, and those types of subjects. And what you're probably not seeing here is when I roll over a little square, there's a pop-up dialog box, like I'm on this transparency for this coming Thursday at 3 a.m. I guess local time. No, that would be during the daytime, I guess. It's saying 13 above average, so the transparency will be above average at that time. So let's go a period of darkness, maybe Thursday night at 2200. So it's giving me here information that my limiting magnitude is magnitude 6.3. Oh, that's relative to darkness. Let's go up one to seeing. It's forecasting that my seeing conditions at 2200 this coming Thursday night is going to be good 4 of 5. So I'd probably like to see a 2 there, I think. Again, I'll read their definitions below to see to understand the of 5 scale a little bit better. And then if I go up to transparency at 2200, it's telling me I'm going to have above average transparency. So again, hopefully some of this made sense. It's the first part of the series that I'd like to put together on how I'm getting to the decision of buying the camera that I'm going to buy. Again, I just want to leave you with, use what you have. Get out there, start producing images, start your way up the learning curve, and then as you start to see the images that you're producing, make some judgments about them, and then adjust accordingly. And oftentimes that adjusting accordingly is based upon your budget and really how high you set your standards. I think the important thing is to have fun, learn, adjust, and share your knowledge with others. Other than that, I don't have a whole lot to say, so thank you for dropping into the channel. If you have comments and questions, please put them below. And thanks again. Till next time.